In the vast expanse of the galaxy, long before the sun existed, there was only darkness and a silent ocean of gas. These regions, known as giant molecular clouds, drifted through space as immense, cold reservoirs of matter. They were composed primarily of hydrogen and helium, the most abundant elements in the universe, remnants from the earliest moments after the Big Bang. Within these clouds, temperatures were extremely low, often just a few degrees above absolute zero. In such conditions, atoms could bind together to form molecules, and dust grains, microscopic particles of heavier elements, floated between them. Though sparse by earthly standards, these clouds contained enough material to create thousands of stars. But for long periods, nothing happened. Gravity was present but balanced. The cloud remained stable, vast, quiet, and unchanged, until something disturbed the equilibrium. Somewhere nearby, a massive star reached the end of its life. In a violent explosion, a supernova, it released an enormous shock wave that surged through space. As this wave collided with the molecular cloud, it compressed regions of gas and dust, increasing their density. This compression was critical. In certain pockets of the cloud, gravity began to take over. Matter started to clump together, slowly at first, then with increasing intensity. What was once a stable region became unstable, collapsing inward under its own weight. This marked the true beginning of the sun's story. From a cold, diffuse cloud to the first signs of structure. A transformation had begun, one that would ultimately lead to the birth of a star and everything that would follow. In the next stage, this collapsing region will intensify, forming a dense, growing core, the earliest form of the sun itself. The quiet stability of the molecular cloud has now been broken. Within a dense region, gravity begins to dominate. What was once a diffuse collection of gas and dust starts to collapse inward, drawn toward a common center. The process is slow at first, but relentless. As the collapse continues, more and more material is pulled inward. The density rises. Particles that once drifted freely are now packed closer together, their motions becoming increasingly chaotic. With compression comes heat. Every infalling particle transfers energy toward the center, and the core begins to warm. Temperatures climb from just a few degrees above absolute zero to thousands of degrees. Pressure builds alongside it, creating an environment that is no longer calm, but dynamic and evolving. At the heart of this collapsing region, a distinct structure begins to emerge. A central concentration of mass, dense, hot, and growing, forms within the cloud. This is the protostar, the earliest stage of a star's life. It is not yet shining like the sun we know today. There is no nuclear fusion in its core, no true starlight. But it is no longer just a cloud. It has become a defined object, bound together by gravity, radiating heat generated from its own contraction. Around it, material continues to fall inward, feeding the growing core. The protostar becomes brighter, hotter, and more compact as time progresses. This stage marks a critical transition. The sun is no longer just forming, it now exists in its earliest form. But it is still incomplete. To become a true star, the core must reach even higher temperatures, extreme enough to ignite nuclear fusion. And as the collapse continues, the system begins to change in another fundamental way. Rotation will reshape everything. As gravity continues to pull matter inward, another fundamental force begins to shape the system: rotation. Even in its earliest state, the collapsing cloud was not perfectly still. It possessed a slight, almost imperceptible spin. But as the cloud contracts, that rotation begins to accelerate. This is a consequence of a fundamental principle in physics, the conservation of angular momentum. As the radius of the collapsing region decreases, its rotational speed increases. What began as a slow drift becomes a rapid spin. The entire structure transforms, not just collapsing inward, but rotating faster with time. This rotation changes everything. Material can no longer fall directly into the center from all directions. Instead, the inward motion is redirected. Gas and dust begin to spread outward along a plane perpendicular to the axis of rotation. The result is the formation of a flattened, rotating structure, a protoplanetary disk. At the center, the protostar continues to grow, pulling in nearby material. But not all matter can reach it. Much of it remains in orbit circling the central mass within this expanding disk. A clear separation begins to emerge. At the core, a dense, hot protostar, the future sun. Surrounding it, a vast, rotating disk of gas and dust, raw material that will one day form planets, moons, asteroids, and comets. This structure is no longer chaotic. It is organized. A central object dominates, while the remaining matter settles into stable, rotating paths around it. The foundation of an entire solar system has now taken shape. But the transformation is not yet complete. At the center, the protostar continues to heat up. Pressure intensifies. Conditions grow extreme with every passing moment. Soon, the core will reach a critical threshold. And when it does, a new process will begin, one that will turn this forming object into a true star. At the center of the forming system, the protostar continues to evolve. Material from the surrounding disk and collapsing cloud is still falling inward, drawn by gravity toward the growing core. With each addition, the protostar gains mass, and with greater mass comes stronger gravitational force. The collapse does not stop. Instead, it intensifies. As matter accumulates, the core becomes increasingly compressed. Density rises to extreme levels, forcing particles closer together than ever before. The inward pressure grows immense, and with it, the temperature begins to climb rapidly. This heating is not the result of nuclear reactions, not yet. It is driven by gravitational contraction. As the protostar shrinks under its own gravity, gravitational potential energy is converted into thermal energy. Every infalling particle adds to this process, transferring kinetic energy into heat as it collides and compresses within the core. The result is a steadily intensifying environment. Temperatures rise from thousands to hundreds of thousands and eventually toward millions of degrees. The core becomes a dense, searing region of plasma where atoms can no longer remain intact. Hydrogen, the dominant element, exists in an ionized state, its electrons stripped away, forming a highly energetic, electrically charged gas. At the same time, pressure continues to build. The weight of the outer layers presses inward, further compressing the core. This combination of high temperature and immense pressure pushes the protostar closer to a critical threshold, a threshold that defines the birth of a star. For nuclear fusion to begin, the core must become hot and dense enough for hydrogen nuclei to overcome their natural repulsion and collide with enough force to merge. That moment is approaching. The protostar is no longer just forming, it is preparing for ignition. And when that ignition occurs, everything will change. Deep within the core of the protostar, conditions have reached an extraordinary threshold. Temperatures soar into the millions of degrees. pressure becomes almost unimaginable. The core is now a dense, turbulent environment where matter exists in its most extreme state. Here, the fundamental forces of nature begin to compete. Hydrogen nuclei, positively charged protons, are forced so close together that their natural electrical repulsion can no longer keep them apart. The immense pressure and heat overcome this barrier, and then, for the first time, they fuse. Two hydrogen nuclei collide and merge, initiating a chain of reactions that ultimately form helium. This process, known as nuclear fusion, releases an enormous amount of energy. Not from chemical reactions, not from compression alone, but from the conversion of mass itself into energy. A small fraction of matter is lost in the process, transformed directly into energy, according to the fundamental principle of mass-energy equivalence. The result is staggering. An immense potok of energy begins to radiate outward from the core. This energy pushes against the inward pull of gravity, creating a balance, an equilibrium that stabilizes the entire structure. For the first time, the object at the center is no longer collapsing uncontrollably. It has become stable, self-sustaining. A star is born. This moment marks the true birth of the sun. No longer a protostar, it now shines as a fully formed star, powered by continuous nuclear fusion at its core. Light and energy begin their long journey outward, eventually escaping into space. What was once a dark, collapsing cloud now becomes a source of illumination, one that will dominate its surrounding system for billions of years. But while the sun has ignited, its story is far from complete. Around it, the rotating disk of gas and dust continues to evolve, shaping itself into something far more complex. In the next stage, this disk will begin to organize, collide, and grow, forming the foundations of planets. With nuclear fusion now active in its core, the young sun enters a defining phase of its existence. For millions of years, gravity had driven collapse, pulling matter inward, compressing the core to extreme conditions. But now, a new force rises to oppose it: outward pressure. The energy released from nuclear fusion generates an intense potok of radiation and thermal pressure, pushing outward from the core. This outward force begins to counterbalance the inward pull of gravity. At first, the system is unstable, adjusting, oscillating, seeking balance. But gradually, a state of equilibrium is achieved. Gravity pulls inward, pressure pushes outward, and the two forces reach a perfect balance known as hydrostatic equilibrium. This balance stabilizes the sun's structure. The violent collapse ends. The size, temperature, and energy output settle into a consistent state. The sun has now entered the longest and most stable phase of its life, the main sequence. In this stage, nuclear fusion becomes a steady, self-regulating process. Hydrogen nuclei continuously fuse into helium within the core, releasing energy at a nearly constant rate. Each second, vast amounts of hydrogen are converted, sustaining the sun's luminosity for billions of years. The sun is now classified as a G-type main sequence star, a category defined by its mass, temperature, and spectral characteristics. It is no longer forming. It is now fully born, a stable star, radiating energy into space, shaping the environment around it, and establishing dominance over the system that surrounds it. This transition marks a profound shift from chaos to stability, from formation to long-term evolution. But while the sun has reached equilibrium, the surrounding disk has not. Beyond the star, countless particles continue to collide, merge, and grow. The stage is now set for the next transformation, the formation of the protoplanetary disk into worlds. The Sun did not form in isolation. Its origin traces back to a shared environment, one where many stars were born together from the same collapsing molecular cloud. In these regions, star formation does not occur one object at a time, but in groups, clusters of stars emerging almost simultaneously from the same reservoir of gas and dust. The Sun was one of them. Within this stellar nursery, dozens, perhaps hundreds, of stars ignited in close proximity, each formed from neighboring fragments of the same cloud, inheriting a similar chemical composition, primarily hydrogen and helium, but also enriched with heavier elements forged in earlier generations of stars. This chemical fingerprint is one of the key pieces of evidence. The presence of certain heavy elements, such as iron and other metals, suggests that the material which formed the Sun had already been influenced by previous stellar events, including supernova explosions. These events seeded the cloud with enriched matter, leaving behind signatures that are still detectable today. There is also evidence that some stars in our galaxy may be true siblings of the Sun, formed from the same cloud, sharing nearly identical compositions and ages. Though they are now scattered across vast distances, their similarities hint at a common origin. But this clustered beginning did not last. Star clusters are not permanent structures. Over time, gravitational interactions between stars and the broader gravitational influence of the galaxy begin to pull them apart. Slowly, the cluster disperses. Stars drift away from one another, each following its own orbit around the galaxy. What was once a dense, crowded birthplace becomes indistinguishable, a collection of stars spread across thousands of light years. The Sun's siblings are still out there, but they are no longer nearby. Today, the Sun appears isolated, a solitary star in space. Yet its origins tell a different story, one of a shared beginning, shaped within a dynamic and crowded stellar environment. And within that environment, something else was unfolding. Around the young Sun, the remaining disk of material was beginning to transform, colliding, clumping, and evolving into the first building blocks of planets. In the next stage, this disk will give rise to an entirely new structure, the protoplanetary system. With the Sun now stable and shining, the surrounding system begins its next transformation. Encircling the young star is a vast protoplanetary disk composed of gas, dust, and microscopic solid particles. This disk, once part of the collapsing cloud, now becomes the birthplace of an entire planetary system. Within it, motion is constant. Particles collide, stick, and grow. Tiny dust grains merge into larger aggregates. Over time, these clumps become kilometer-sized bodies, planetesimals, the first solid building blocks of planets. The process accelerates. Gravity begins to take over once again, but now on a smaller scale. Larger bodies attract more material, growing rapidly through collisions and accumulation. Some become massive enough to dominate their regions, clearing paths within the disk. These are the early planets. Closer to the Sun, where temperatures are high, only rocky materials can survive. Here, terrestrial planets begin to form. Farther out, where it is colder, gases and ices accumulate, giving rise to massive gas giants and icy worlds. Not all material is incorporated into planets. Some remnants remain scattered, forming asteroids, comets, and other small bodies. These leftover fragments preserve the original composition of the early solar system, acting as time capsules of its formation. At the center of it all, the Sun dominates. Containing nearly all of the system's mass, about 99.86%, its gravitational influence governs every orbit, every collision, and every path taken by the forming bodies. The structure of the solar system is defined by this dominance. Planets settle into stable orbits. Motion becomes predictable. Chaos gives way to order. What began as a collapsing cloud has now evolved into a fully structured system, a star surrounded by worlds. And within this system, conditions will continue to change. Surfaces will cool, atmospheres will form, and on at least one planet, entirely new processes will begin. The story of the Sun's birth is complete, but the story of its system is just beginning.